Hello, computer scientists. So the lecture that we missed is on indexes and keys, or indices and keys, depending on how you want to present it. So it's just a short one that I want to make sure that I cover quickly. So there's basically two kinds of keys. The first one is called automatic keys, or surrogate, or hidden keys. They all three different ways of basically saying the same thing. These keys in your table, in your MySQL tables, are created inside the database, usually automatically, and usually they are hidden from the user. So that's like when you have in your database, you create a column that auto increments and is usually called a key or an ID or something like that. But it really has no connection to the data itself. So the number is not related to the rest of the data in any way. One advantage to it is it's really fast to create and very easy to understand. And so usually it's just integers, starts at 0 and automatically increments 1, 2, 3, 4, 5, 6, 7 every time you add a new row. Doesn't rely on any business logic, so if you change your columns, if you change your tables, whatever, your key happily just keeps on auto-incrementing and adding new unique IDs at the end. But one of the big downsides to it is it's really hard to combine if you have multiple databases, right? So if you merge with another company or something like that, and you are both using automatic keys for your customers, then you're going to have two customer twos. You're going to have a whole bunch of sales to customer number 2, and you won't know which customer number 2 it is. Or you might have books checked out to customer number 67, and if all of your libraries in your library system use automatic keys, they're each going to have their own customer number 67. So they're really easy to use, really easy to understand, really easy to implement, fast to create, fast to use, really easy to use in code as well. The one downside being that they're really hard to integrate with each other. The other kind of keys are natural intelligent domain keys. And you can find a key that is already unique and is relevant to the domain. So this is something like your student ID. This is relevant to you because it is unique to you. Often it will actually be relevant in the sense of an email address because it's something that you use, something you remember, something that has your name as part of it. It makes sense to both you and the developer and the business to use your name, your email address. You know that if there's a J Bartus at Winona, there's probably not going to be any other J Bartuses at Winona. But it also makes it pretty easy. Even if you do have a J Bartus, you can make it, J Bartus 2 or J A Bartus or something like that. Makes it really hard to change though, right? Because once you have that key everywhere, it is kind of, you're locked into it. It is your business logic. Student employee email address, as you know, most websites now use your email address. A lot of websites are moving away from IDs and just using email addresses. Because why? Why create an ID that is fake when you already have something unique to that person, which is their email address? Social security number, is pretty universally unique, hopefully is unique. The libraries use ISBN numbers, stores use SKUs, the barcodes when you go shopping, those are all unique. Of course, you might need to get a little bit more complicated. You can have combined keys. So for example, if you have a Facebook user or Twitter or Instagram or whatever you're using, their user ID isn't enough to identify all their posts. Even the title might not be enough, right? Because, you know, maybe you go to the beach and so you have several post titles, beach day, and you might need date and time or something like that. And so you can combine several columns together to make a natural domain key, because the combination of user ID, post title, date and time is obviously going to be unique and relevant to the domain and relevant to the subject. Obviously, it makes it really hard to change that underlying data if you're using it as part of your key. There is one other kind of key that I don't mention here, which is kind of an automatic key, and that is a guaranteed unique ID. So that is something that you can use automatically. It'll create, you know, say a 100 and something character long guaranteed unique ID. As you can imagine, with uppercase, lowercase, and numbers, alone without even symbols, you have 52 options for every character. So if it's 100 characters long, that's 52 to the power of 100, which is, I think, more than grains of sand in the universe or something like that. So you can make sure that it's unique. So one of the problems that you might come across that I mentioned earlier is two companies merge and your IDs are not unique. So say you have John Doe at the old company A and Jane Doe at the old company B. You know, they both have the same ID number. They might have slightly different email addresses, jdoe@a.com or jdoe@b.com, but what do you do with the new company? You know, especially since the old employee ID is probably literally in dozens, if not hundreds of tables, because it used to be the unique key, right? So if this employee has payroll and vacation and benefits and time off and, you know, their daily, you know, their card swiping and all this stuff is going to go off their ID. So how do you combine you know, these two IDs? One option is, again, a multi-column index. So you could have employee ID and their subsidiary ID. So if it used to be a.com, you know, maybe you have JD123-A and JD123-B. But then again, you have to add that to all the tables. And do you add it to all the users? What about new users? Would they be JDoe at, you know, -N or something like that? I don't know. You know, these are hard problems to fix, and so they're ones that, you know, you need to consider when you are creating your database. I mean, obviously, you're not going to sit there and worry about your company being taken over by a larger company when you're just starting out. That's not realistic. That's not how database designers work. But it's something that I want you to be aware of as somebody that is studying databases. Is, you know, these are the things that database designers think about when they're thinking about indices and keys. So I want to just quickly show you as well how indices and keys work. All right, so here we have a table that I drew up. I love graph paper, it's like my favorite thing. So I have a first name, a last name, and an address, and we're trying to figure out how basically the data structure of keys work. So obviously, if you have a column here first, you know, that is ID, 0, 1, 2, blah, 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 that makes it pretty easy. All of these will be sorted according to the primary key. But say I know that I sort a lot on last name for whatever reason, and so I want to add another key or an index on this field right here on last name. So what happens when I do that is basically it creates a tree that sorts all of these for me. So you guys are all familiar with binary trees by now. So let me add a third person here, Alex Rodriguez, and he lives at 88 something something something, right? So I'm adding my key here, and I have Smith, Blaine, Cruz, and Rodriguez. But what I'm going to do is go through this data, right? And I'm going to sort it here. So I have my keys over here, and the data that I'm sorting by over here. So I have to go through all my data and build up this tree. So I'm going to have Smith is going to be first. And as I build my tree, I probably am not even going to put Smith there. I'm just going to put the key. So that's going to be 0. And then I'm going to hit Blaine. So Blaine's going to be over here, number 1. So this is all the bottom of my tree here. And then I have Cruz, which is number 2. And here I have Rodriguez, number 3. So you can see, even though I keep my IDs here, right, I wouldn't even store the names there. I just wrote them down there so you can see they're in alphabetical order. If I need to find Cruz, in this table here, every time I was searching on a surname, I would have to start at the first one and just go through linearly. So if I have 1,000,000 names, on average, right, I'm going to have to search 500,000 records to find the one I'm looking for. Sometimes it'll be at the top, sometimes it'll be at the bottom. On average, it's going to be 500,000 records. Whereas if I can just put a data structure in front of it, right, I'm not restoring all the data. All I'm doing is building a tree with pointers, right, into the locations of my data. So all the data is still only stored in one place. It's just that now I have another binary tree here that is sorted according to my new key. So that way, if I'm looking for Rodriguez, right, I have 1, 2 steps to search. If I'm looking for Cruz, 1, 2 steps to search. Blaine, 1, 2, Smith, 1, 2, right? So it's log base 2 of n, however many things I have. So instead of always being a half, right? So if I only have 4 things, it's the same, right? But this is going to grow linearly with the amount of data I have, and this here is going to grow a lot smaller. So I'm going to have a far fewer steps, right? Here, I'll give you an example. 1024. Say I only have, just over 1,000 rows in my table, right? So I'm going to have to, on average, search 512 rows. If I don't have a key, every single time I look up somebody's last name, I'm going to have to look through 512 rows. If I set up this binary tree here, 10 rows. That's all I have to search, because it's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. To the bottom of the tree. So this obviously is a lot faster than this. And as you get higher and higher and higher, it gets even faster, right? 1,000,000 rows, instead of having 500,000 to search, I have 20 to search, right? 1,000,000,000 is 30, and so on and so on and so on. So this, adding a key to whatever data you're searching on, right, makes searches a lot faster. Of course, that has a cost, doesn't it, right? So what happens if I have to insert something, or if I delete something? Then I need to rebalance my tree, right? And so if rebalancing your tree is very, very expensive, and you have to do it a lot, then you really have to be careful with how many keys you have, right? If mostly what you do is search, and mostly what you do is search on last name, then adding a key here makes a lot of sense, right? So that would make sense, for example, in a university database is a great example, right? Because I probably am looking up people's last names or, you know, their first names probably to enter grades, right? I'm probably sorting by these two columns a lot in D2L. So it makes sense to have these keys, because how often am I going to add a new user, right? You're going to do this once in September. You're going to add a, you know, few thousand users, and then maybe during the school year you'll add 1 or 2 or 3 a week, something like that, or delete 1 or 2 or 3. It's not something that's going to happen very often, right? So having these keys makes a lot of sense, because the benefit of this log base 2 searching far outweighs the detriment of having to rebalance your tree if you delete or insert a new user. And that is how they work. If you have any questions, feel free to email me or hit me up on Discord. Thanks.